Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we solved some problems to obtain the Z transform of some useful sequences, and also we solved some problems to apply properties on the Z transform. In today's video lecture, we'll be discussing inverse Z transform. Z transform for a discrete time sequence x of n is defined as x of z equals to summation n minus infinity to plus infinity x of n z to the power minus n. This is the forward transform which converts time domain signal into frequency domain signal. And inverse z transform is the one which converts frequency domain signal x of z to a time domain signal x of n. And this inverse z transform can be obtained by three methods. First one is power series expansion method, second one is partial fraction expansion method, and third one is the contour integration method. In the following section, we'll be studying the three methods one by one. We'll be starting with the first method, which is power series expansion method. By definition, the Z transform is expressed as x of z equals to summation n minus infinity to plus infinity x of n z to the power minus n. If we expand this summation, which will be infinite in nature, there will be only two terms for each iteration. One of the term will be x of n, which will be the discrete time sequence itself, and the other term will be the z variable, which is used for Z transform. If we have a Z transform for any discrete time sequence, and if we are able to successfully express that Z transform in the following nature, then by just looking at the constant associated with the Z variable, we can approximate or we can write the discrete time sequence. So we'll be obtaining time domain sequence from the frequency domain signal x of z. And this in power series expansion method will be obtaining discrete time sequence or will be recovering discrete time sequence from the Z transform by long division method. So from this expansion of the summation, we'll just write the constants associated with the Z variables. It will give us the discrete time sequence x of n. So in power long division method, Z transform will be expressed as ratio of polynomials, numerator polynomial in Z and denominator polynomial in Z. And numerator will be divided by the denominator. By doing this, we'll be getting the expansion or a polynomial, resultant polynomial in Z, and the constants associated with each term will be the discrete time sequence that we'll have to get for. We'll consider an example to understand this power series expansion method, and the statement is determine inverse Z transform of the Z transform x of z equals to 2 plus Z inverse divided by 1 minus half Z inverse with region of convergence mod of Z greater than half. So we'll start the long division method. We'll write 2 plus Z inverse and we'll divide it by 1 minus half Z inverse. First we'll multiply 2 to 1 minus half Z inverse. We'll get 2 minus Z inverse. We'll subtract the terms. Plus 2 and minus 2 will cancel out. We'll remain with 2Z inverse. So to obtain 2Z inverse from 1 minus half Z inverse, we'll multiply 2 to it. So we'll get 2Z inverse minus Z to the power minus 2. Cancelling out the similar terms, we'll remain with Z to the power minus 2. And we'll keep on doing this. By doing this, we can get either a infinite series or a finite series. And for this example, the series that we obtained is 2 plus 2Z inverse plus Z to the power minus 2 plus half multiplied by z to the power minus 3 plus 1 by 4 multiplied by z to the power minus 4, and this continues. If this is the way of expressing the z transform from the ratio of two polynomials, then constants associated with each of the z term will be representing the discrete time sequence. So discrete time sequence x of n will be equals to 2, 2, 1, half, 1 by 4, and so on. This is an infinite series. And the second method to obtain the inverse z transform is partial fraction expansion method. Now, popularly, partial fraction expansion method is applied when x of z is expressed in terms of rational. And if x of z is rational, inversion simply means expanding x of z in partial fraction form, as we already know what is partial fraction and we have used it many a times. So in partial fraction form, the z transform x of z will be expressed as summation I equals to 1 to m ai. Capital AI is the residue for the root small ai, and we'll have to find these residues capital AI for each of the root in the denominator, which will be expressed by small lowercase ai. So capital AI divided by 1 minus lowercase ai z inverse. Now if region of convergence, and the concept is very simple. If you observe the term inside the summation, it is like expressing, or it is like obtaining the z transform of the standard function for which we have solved the problem earlier. If we are able to express any z transform in the following manner, then by looking at the region of convergence, we'll be able to write its equivalent discrete time expression. For example, if region of convergence of the given z transform x of z, if it is outside the pole at z equals to ai, then the inverse z transform of this term have to be a right-sided sequence, which will be defined as capital AI, which is the residue that we'll have to find, multiplied by small ai to the power n u of n. Or if the region of convergence of the z transform is inside the pole at z equals to ai, then it has to be a left-sided sequence. So its inverse transform will be minus capital AI small ai to the power n u of minus n minus 1, which represents the left-sided sequence. So to apply partial fraction expansion method, we'll be following the mentioned steps here. In the first step, we'll rearrange the given z transform x of z as x of z divided by z. By doing this, on the right hand side, we'll be easily able to express each of the root in the denominator as the partial fraction form. So capital x of z divided by z equals to numerator polynomial divided by, will factorize the denominator. So each factor will be associated or will be given a residue. In the second step, x of z divided by z will be, each root in the denominator will be assigned one residual. Capital A1 is residue, which is associated with the pole P1, plus A2, the second residue associated with the pole P2, plus A3 z divided by P3, and so on. This depends on the number of poles that we get, where each residue will be obtained by multiplying the pole associated with it to x of z divided by z, where z value will be equal to the pole pk. So ak will be z minus pk of x of z divided by z if z is equal to pk, and k depends on the number of poles. Now there is a possibility of obtaining repeated poles in the denominator, or repeated poles or repeated root in the denominator. If we get a repeated root as expressed here, x of z divided by z equals to numerator polynomial divided by z minus p to the power n, or z minus p to the power n. P is a repeated pole here, and it has been repeating for n times because n is the power. In that case, the partial fraction expansion form will be a1, which is the residue, divided by z minus p, plus a2 divided by z minus p whole square, plus so on up to an divided by z minus p to the power n. Now n represents the number of repetitions of the pole, and we'll obtain the residues ak for repeated poles as 1 divided by n minus k factorial, and we'll take the derivative of the procedure that we used to find the residue earlier. And the number of derivative again depends on the number of repetition of the pole. So dn minus k divided by dn minus k multiplied by z, dn minus k divided by dz to the power n minus k multiplied by z of z minus p to the power n x of z divided by z, where z will be equals to value of the pole p. After obtaining the residues, we'll rearrange the z transform in the equation 1 as x of z equals to a1z divided by z minus p1 plus a2z divided by z minus p2, and so on till the last value. Or if we have a repeated pole, then it will be, or to express the z transform in the inverse, the negative powers of the z, we can rearrange the above equation as a1 divided by 1 minus p1 z inverse plus a2 divided by 1 minus p2 z inverse plus 1 up to last value an divided by 1 minus pn z inverse. And in step number 4, each of the term represented above are of the standard z transform representation, ak divided by 1 minus pk z inverse. Now depending upon the region of convergence for the given z transform, the following standard z transform pair must be used. Now we have been doing this. We did both of these examples earlier 2 times. So for a right-sided sequence, if we have a sequence, right-sided sequence defined as pk to the power n u of n, then its z transform will be of the form 1 divided by 1 minus pk z inverse for the region of convergence mod of z greater than a, or for the causal sequence. Causal sequence is nothing but the right-sided sequence. If the sequence is left-sided, then its z transform will be 1 divided by 1 minus pk z inverse itself, but the region of convergence mod of z will be less than mod of a. This will be a non-causal sequence. So its equivalent representation that we'll be using is minus pk to the power n u of minus n minus 1. So we'll be following these 4 steps to obtain the inverse z transform by using partial fraction expansion method. We'll consider an example. Determine inverse z transform of x of z defined as x of z equals to 1 divided by 1 minus 1.5 z inverse plus 0.5 z to the power minus 2. We'll have to obtain the inverse z transform for 3 different region of convergences. First region of convergence where mod of z will be greater than 1. Second region of convergence value where mod of z less than 0.5. And third region of convergence where mod of z will be greater than 0.5 but less than 1. So in the very first step, we'll rearrange the given z transform to have positive powers of z. So x of z will be equals to z square divided by z square minus 1.5 z plus 0.5. And by the first step of partial fraction form, we'll express the given z transform x of z as x of z divided by z. So one of the z from the numerator will be sent to the other side. So we'll get x of z divided by z, which will be equals to z divided by z square minus 1.5 z plus 0.5. Now we'll factorize the denominator, which will give us z divided by z minus 1, which is one of the root, and z minus 0.5, which is the second root. So because there are two roots or two poles, we'll be assigning two residues, a and b. So x of z divided by z will be equals to a divided by z minus 1 plus b divided by z minus 0.5. Now we'll calculate the value of a and b with the help of x of z divided by z. Now to find or to calculate capital A, the pole associated with it will be multiplied to x of z divided by z, and we'll substitute z as 1. Simplifying this, the value of a will be getting is 2. Likewise, for the second residue b, will multiply the pole associated with it to x of z divided by z, where z will be equals to 0.5. Simplifying it, will get minus 1. So using 2 and minus 1 in place of a and b in the above equation, we can rewrite it as x of z divided by z equals to 2 divided by z minus 1 minus of 1 divided by z minus 0.5, or multiplying z, the value of z which is in the denominator on left hand side, to the right hand side, we'll be able to express it as x of z equals to 2z divided by z minus 1 minus z divided by z minus 0.5. Or expressing this z transform in negative powers of z, we can rewrite it as 2 divided by 1 minus z inverse minus 1 divided by 1 minus 0.5 z inverse. Now this is the standard way of representing the z transform. Now depending on the region of convergence that we are evaluating the z transform in, the representation of its discrete time sequence will change. So the first region of convergence we'll be considering in is if mod of z is greater than 1. Now there are two poles, z equals to, there are two poles, z equals to 1 and z equals to 0.5. So the region of convergence, the first region of convergence will be taking is greater than 1 of the pole. If z value is greater than 1 means, on the right hand side we have drawn a z plane. There will be two circles, one circle drawn with a radius of 0.5, which is one of the pole, and another circle which will be drawn with a radius of 1. So if mod of z, if it is greater than 1, then the region of convergence will be exterior to the outer circle. If it is exterior to the outer circle, then it has to be a right-sided sequence. So 2 divided by 1 minus z inverse will be represented as 2, the multiplying factor of the value of residue a, 1 to the power n u of n, minus second term 1 multiplied by 0.5 to the power n u of n, because for this region of convergence the sequence will be a right-sided sequence. Taking u of n common, the discrete time sequence x of n can be rewritten as 2 minus 0.5 to the power n whole multiplied by u of n. Now if we consider the region of convergence for z values less than 0.5, then again on the right hand side I have drawn a z plane. We'll be having two circles with the radius of two poles, one the inner circle with the radius of 0.5 and the outer circle with an radius of 1. If mod of z, if it is less than 0.5, then the region of convergence will be inside of the first circle or inside of the inner circle whose radius is 0.5. Now this means the discrete time sequence has to be a left-sided sequence. Now for left-sided sequence, the time domain representation of the given Z transform 2 divided by 1 minus Z inverse will be 2 minus 1 to the power n u of minus n minus 1 minus minus 0.5 to the power n u of minus n minus 1, or taking u of minus n minus 1 common, we can rewrite it as minus 2 plus 0.5 to the power n. And if we consider the third case, where the region of convergence is greater than 0.5 but less than 1, then on the z plane the region of convergence will be between two circles. Now if this is the case, then the first term in the Z transform, that is 2 divided by 1 minus Z inverse, will be non-causal. And the second term 1 divided by 1 minus 0.5 Z inverse will be a causal, because region of convergence is outside 0.5, so it has to be a right-sided sequence, and region of convergence is inside 1, so it has to be a left-sided sequence. Therefore, discrete time sequence x of n can be written as 2 minus 1 to the power n u of minus n minus 1 minus 0.5 to the power n u of n. So these are the discrete time sequences for the same Z transform depending on the region of convergence. The next problem we'll be considering is, we'll obtain the inverse Z transform for the Z transform defined as 1 divided by 1 plus Z inverse multiplied by 1 minus Z inverse whole square for the region of convergence mod of Z greater than 1. In the given Z transform, one of the pole is repeated. There are two poles, Z equals to minus 1 and Z equals to plus 1, and the pole Z equals to plus 1 is repeated 2 times. So expressing the given Z transform in the positive powers of Z, we can rewrite it as Z cube divided by Z plus 1 Z minus 1 whole square. Again expressing x of Z divided by Z, numerator will be Z square this time, divided by Z plus 1 Z minus 1 whole square. Now because Z equals to 1 is repeating, the partial fraction approach will be the second method that we saw. X of Z divided by Z equals to first residue. A1 will be assigned to a distinct pole, which is Z plus 1, plus A2. Second residue will be applied to the repetition Z minus 1, plus A3. Third residue will be applied to the repeated pole Z minus 1 whole square. To find A1, A2, A3, A1 will be obtained by multiplying the pole associated with it, that is Z plus 1 to x of Z divided by Z, where Z will be equals to minus 1. Simplifying this, will get 1 by 4. Next, we'll obtain the residue of the repeated root A3, where Z minus 1 whole square will be multiplied to Z x of Z divided by Z. Simplifying this, will get 1 by 2. Now to obtain the residue A2, we'll have to differentiate A3 and then take or apply Z equals to 1. So first we'll multiply Z minus 1 whole square to x of Z divided by Z. So we'll obtain Z square divided by Z plus 1. Now we'll differentiate this by applying u by v4. We'll get Z plus 1 of 2Z minus Z square divided by Z plus 1 whole square. If we substitute Z equals to 1 in this expression, we'll get 3 divided by 4. Now we are only differentiating it once because the pole has been repeated twice. The power of on the repeated pole is 2. So it will be n minus k, or n minus k will be equals to 1. So we'll be differentiating it once. Now using the value of the residues in the Z transform expression, we can write it as x of Z divided by Z equals to 1 by 4 divided by Z plus 1, 3 by 4 divided by Z minus 1, plus half divided by Z minus 1 whole square. Or expressing it in the negative power of Z, it will be 1 by 4 divided by 1 plus z inverse plus 3 by 4 divided by 1 minus z inverse plus half z inverse divided by 1 minus z inverse whole square. Now because region of convergence is mod of z greater than 1, we for repeated poles we use the Z transform expression as n pk to the power n u of n's Z transform will be pk z inverse divided by 1 minus pk z inverse whole square. So using this expression, x of n, the discrete time sequence will be obtaining is 1 by 4 minus 1 to the power n un plus 3 by 4 1 to the power n un plus half n multiplied by 1 to the power n u of n. Region of convergence mod of z greater than mod of pk, or taking u of n common, discrete time sequence x of n can be written as 1 by 4 of minus 1 to the power n plus 3 by 4 plus 1 by 2 n of u of n. So these are the two concepts from which we can obtain inverse Z transform. The third one, contour integration method, will be discussing in the next video lecture. If you have any doubts, you can contact me. Thank you all.